Graphite, rare 4T, archaically referred to as Plumbago, is a crystalline form of carbon, a semi-metal, a native element mineral, and one of the allotropes of carbon. Graphite is the most stable form of carbon under standard conditions. Therefore, it is used in thermochemistry as the standard state for defining the heat of formation of carbon compounds. Graphite may be considered the highest grade of coal, just above anthracite and alternatively called metaanthracite, although it is not normally used as fuel because it is difficult to ignite. Types and varieties. There are three principal types of natural graphite, each occurring in different types of ore deposit. Crystalline flake graphite occurs as isolated, flat, plate-like particles with hexagonal edges if unbroken, and when broken the edges can be irregular or angular. Amorphous graphite. Very fine flake graphite is sometimes called amorphous in the trade. Lump graphite occurs in fissure veins or fractures and appears as massive platy intergrowths of fibrous or acicular crystalline aggregates, and is probably hydrothermal in origin. Highly ordered pyrolytic graphite, or more correctly highly oriented pyrolytic graphite, refers to graphite with an angular spread between the graphite sheets of less than 1 degree. The name graphite fiber is also sometimes used to refer to carbon fiber or carbon fiber reinforced polymer. Occurrence. Graphite occurs in metamorphic rocks as a result of the reduction of sedimentary carbon compounds during metamorphism. It also occurs in igneous rocks and in meteorites. Minerals associated with graphite include quartz, calcite, micas and tourmaline. In meteorites it occurs with troilite and silicate minerals. Small graphitic crystals in meteoritic iron are called cliftonite. According to the United States Geological Survey, world production of natural graphite in 2012 was 1,100,000 tons, of which the following major exporters are China, India, Brazil, North Korea and Canada. Graphite is not mined in the United States, but U.S. production of synthetic graphite in 2010 was 134 knots, valued at $1.07 billion. Properties. Structure. Graphite has a layered, planar structure. In each layer, the carbon atoms are arranged in a honeycomb lattice with separation of 0.142 nanometers, and the distance between planes is 0.335 nanometers. Atoms in the plane are bonded covalently, with only 3 of the 4 potential bonding sites satisfied. The fourth electron is free to migrate in the plane, making graphite electrically conductive. However, it does not conduct in a direction at right angles to the plane. Bonding between layers is via weak van der Waals bonds, which allows layers of graphite to be easily separated, or to slide past each other. The two known forms of graphite, alpha and beta, have very similar physical properties, except the graphene layers stack slightly differently. The hexagonal graphite may be either flat or buckled. The alpha form can be converted to the beta form through mechanical treatment, and the beta form reverts to the alpha form when it is heated above 1,300 degrees Celsius. Scanning tunneling microscope image of graphite surface atoms. Graphite's unit cell. Animated view of the unit cell in 3 layers of graphene. Ball and stick model of graphite. Side view of layer stacking. Plane view of layer stacking. Rotating graphite stereogram. Other properties. The acoustic and thermal properties of graphite are highly anisotropic, since phonons propagate quickly along the tightly bound planes, but are slower to travel from one plane to another. Graphite's high thermal stability and electrical conductivity facilitate its widespread use as electrodes and refractories in high-temperature material processing applications. However, in oxygen-containing atmospheres, graphite readily oxidizes to form CO2 at temperatures of 700 degrees Celsius and above. Graphite is an electric conductor, consequently, useful in such applications as arc lamp electrodes. It can conduct electricity due to the vast electron delocalization within the carbon layers. These valence electrons are free to move, so are able to conduct electricity. However, the electricity is primarily conducted within the plane of the layers. The conductive properties of powdered graphite allows its use as pressure sensor in carbon microphones. Graphite and graphite powder are valued in industrial applications for their self-lubricating and dry lubricating properties. There is a common belief that graphite's lubricating properties are solely due to the loose interlamellar coupling between sheets in the structure. However, it has been shown that in a vacuum environment, graphite is a very poor lubricant. This observation led to the hypothesis that the lubrication is due to the presence of fluids between the layers, such as air and water, which are naturally absorbed from the environment. This hypothesis has been refuted by studies showing that air and water are not absorbed. Recent studies suggest that an effect called superlubricity can also account for graphite's lubricating properties. The use of graphite is limited by its tendency to facilitate pitting corrosion in some stainless steel, and to promote galvanic corrosion between dissimilar metals. It is also corrosive to aluminium in the presence of moisture. For this reason, the U.S. Air Force banned its use as a lubricant in aluminium aircraft, and discouraged its use in aluminium-containing automatic weapons. Even graphite pencil marks on aluminium parts may facilitate corrosion. Another high-temperature lubricant, hexagonal boron nitride, has the same molecular structure as graphite. It is sometimes called white graphite due to its similar properties. When a large number of crystallographic defects bind these planes together, graphite loses its lubrication properties and becomes what is known as pyrolytic graphite. It is also highly anisotropic and diamagnetic, thus it will float in mid-air above a strong magnet. If it is made in a fluidized bed at 1000 to 1300 degrees Celsius, then it is isotropic turbostratic, and is used in blood-contacting devices like mechanical heart valves and is called pyrolytic carbon, and is not diamagnetic. Pyrolytic graphite and pyrolytic carbon are often confused but are very different materials. Natural and crystalline graphites are not often used in pure form as structural materials, due to their shear planes, brittleness and inconsistent mechanical properties. History of natural graphite use. In the 4th millennium BC, during the Neolithic age in southeastern Europe, the Merita culture used graphite in a ceramic paint for decorating pottery. Sometime before 1565, an enormous deposit of graphite was discovered on the approach to Greenock from the hamlet of Seathwaite in Borrowdale parish, Cumbria, England, which the locals found very useful for marking sheep. During the reign of Elizabeth I, Borrowdale graphite was used as a refractory material to line molds for cannonballs, resulting in rounder, smoother balls that could be fired farther, contributing to the strength of the English Navy. This particular deposit of graphite was extremely pure and soft, and could easily be broken into sticks. Because of its military importance, this unique mine and its production were strictly controlled by the Crown. Other names historically, graphite was called black lead or plumbago. Plumbago was commonly used in its massive mineral form. Both of these names arise from confusion with the similar-appearing lead ores, particularly galena. The Latin word for lead, plumbum, gave its name to the English term for this grey metallic sheened mineral and even to the leadworts or plumbagos, plants with flowers that resemble this color. The term black lead usually refers to a powdered or processed graphite, matte black in color. Abraham Gottlob Werner coined the name graphite in 1789. He attempted to clear up the confusion between molybdenum, plumbago and black lead after Carl Wilhelm Scheele in 1778 proved that there are at least 3 different minerals. Scheele's analysis showed that the chemical compounds molybdenum sulfide, lead sulfide and graphite were 3 different soft black minerals. Uses of natural graphite. Natural graphite is mostly consumed for refractories, batteries, steelmaking, expanded graphite, brake linings, foundry facings and lubricants. Graphene, which occurs naturally in graphite, has unique physical properties and is among the strongest substances known. However, the process of separating it from graphite will require more technological development. Refractories. This end use began before 1900 with the graphite crucible used to hold molten metal. This is now a minor part of refractories. In the mid-1980s, the carbon magnesite brick became important, and a bit later the alumina graphite shape. Currently the order of importance is alumina graphite shapes, carbon magnesite brick, monolithics, and then crucibles. Crucibles began using very large flake graphite, and carbon magnesite brick requiring not quite so large flake graphite. For these and others there is now much more flexibility in size of flake required, and amorphous graphite is no longer restricted to low-end refractories. Alumina graphite shapes are used as continuous casting ware, such as nozzles and troughs, to convey the molten steel from ladle to mold, and carbon magnesite bricks line steel converters in electric arc furnaces to withstand extreme temperatures. Graphite blocks are also used in parts of blast furnace linings where the high thermal conductivity of the graphite is critical. High-purity monolithics are often used as a continuous furnace lining instead of the carbon magnesite bricks. The US and European refractories industry had a crisis in 2000 to 2003, with an indifferent market for steel and a declining refractory consumption per ton of steel underlying firm buyouts and many plant closures. Since much of the lost capacity was for carbon magnesite brick, graphite consumption within refractories area moved toward alumina graphite shapes and monolithics, and away from the brick. The major source of carbon magnesite brick is now imports from China. Almost all of the above refractories are used to make steel and account for 75% of refractory consumption. The rest is used by a variety of industries, such as cement. According to the USGS, U.S. natural graphite consumption in refractories was 12,500 tons in 2010. Batteries. The use of graphite in batteries has been increasing in the last 30 years. Natural and synthetic graphite are used to construct the anode of all major battery technologies. The lithium-ion battery utilizes roughly twice the amount of graphite than lithium carbonate. The demand for batteries, primarily nickel metal hydride and lithium-ion batteries, has caused a growth in graphite demand in the late 1980s and early 1990s. This growth was driven by portable electronics, such as portable CD players and power tools. Laptops, mobile phones, tablet, and smartphone products have increased the demand for batteries. Electric vehicle batteries are anticipated to increase graphite demand. As an example, a lithium-ion battery in a fully electric Nissan Leaf contains nearly 40 kilograms of graphite. Steelmaking. Natural graphite in this end use mostly goes into carbon raising in molten steel, although it can be used to lubricate the dies used to extrude hot steel. Supplying carbon raisers is very competitive, therefore subject to cutthroat pricing from alternatives such as synthetic graphite powder, petroleum coke, and other forms of carbon. A carbon raiser is added to increase the carbon content of the steel to the specified level. An estimate based on USGS US graphite consumption statistics indicates that 10,500 tons were used in this fashion in 2005. Brake linings. Natural amorphous and fine flake graphite are used in brake linings or brake shoes for heavier vehicles, and became important with the need to substitute for asbestos. This use has been important for quite some time, but non-asbestos organic compositions are beginning to reduce graphite's market share. A brake lining industry shakeout with some plant closures has not been beneficial, nor has an indifferent automotive market. According to the USGS, U.S. natural graphite consumption in brake linings was 6,510 tons in 2005. Foundry facings and lubricants. A foundry facing mold wash is a water-based paint of amorphous or fine flake graphite. Painting the inside of a mold with it and letting it dry leaves a fine graphite coat that will ease separation of the object cast after the hot metal has cooled. Graphite lubricants are specialty items for use at very high or very low temperatures, as forging dye lubricant, an anti-seize agent, a gear lubricant for mining machinery, and to lubricate locks. Having low-grit graphite, or even better no-grit graphite, is highly desirable. It can be used as a dry powder, in water or oil, or as colloidal graphite. An estimate based on USGS graphite consumption statistics indicates that 2,200 tons was used in this fashion in 2005. Pencils, the ability to leave marks on paper and other objects, gave graphite its name, given in 1789 by German mineralogist Abraham Gottlob Werner. It stems from graphein, meaning to write, draw in ancient Greek. From the 16th century, pencils were made with leads of English natural graphite. But modern pencil lead is most commonly a mix of powdered graphite and clay. It was invented by Nicolas Jacques Conté in 1795. It is chemically unrelated to the metal lead, whose ores had a similar appearance, hence the continuation of the name. Plumbago is another older term for natural graphite used for drawing, typically as a lump of the mineral without a wood casing. The term plumbago drawing is normally restricted to 17th and 18th century works, mostly portraits. Today, pencils are still a small but significant market for natural graphite. Around 7% of the 1.1 million tons produced in 2011 was used to make pencils. Low-quality amorphous graphite is used and sourced mainly from China. Other uses: natural graphite has found uses in zinc-carbon batteries, in electric motor brushes, and various specialized applications. Graphite of various hardness or softness results in different qualities and tones when used as an artistic medium. Railroads would often mix powdered graphite with waste oil or linseed oil to create a heat-resistant protective coating for the exposed portions of a steam locomotive's boiler, such as the smoke box or lower part of the firebox. Expanded graphite. Expanded graphite is made by immersing natural flake graphite in a bath of chromic acid, then concentrated sulfuric acid, which forces the crystal lattice planes apart, thus expanding the graphite. The expanded graphite can be used to make graphite foil or used directly as hot top compound to insulate molten metal in a ladle or red-hot steel ingots and decrease heat loss, or as fire stops fitted around a fire door or in sheet metal collars surrounding plastic pipe, or to make high-performance gasket material for high-temperature use. After being made into graphite foil, the foil is machined and assembled into the bipolar plates in fuel cells. The foil is made into heat sinks for laptop computers, which keeps them cool while saving weight, and is made into a foil laminate that can be used in valve packings or made into gaskets. Old-style packings are now a minor member of this grouping. Fine flake graphite in oils or greases for uses requiring heat resistance. A GAN estimate of current U.S. natural graphite consumption in this end use is 7,500 tons. Intercalated graphite. Graphite forms intercalation compounds with some metals and small molecules. In these compounds, the host molecule or atom gets sandwiched between the graphite layers, resulting in a type of compounds with variable stoichiometry. A prominent example of an intercalation compound is potassium graphite, denoted by the formula Kc8. Graphite intercalation compounds are superconductors. The highest transition temperature Tc equals 11.5 K is achieved in Ca6, and it further increases under applied pressure.